Hello everyone. The title of our paper is Leveraging Sparse Annotation for Leukemia Diagnosis on the Large Leukemia Dataset. My name is Abdul Rahman and this work is a collaborative effort with my colleague Talha, my PhD advisor Dr. Mohsen Ali and Dr. Waqas Sultani, including the hematologist Dr. Aisha and Dr. Ayman from the Chuktai lab. This work was carried out under the guidance of Dr. Mubarak Shah from the Center of Research in Computer Vision at the University of Central Florida. In this research, we have collected a novel large-scale multi-domain microscopy image dataset from the peripheral blood films of the leukemia patient. In this dataset, we have captured the 28,000 images of microscopic field of view comprising 88K white blood cells. The hematologist carried WBC into 14 types along with 7 explainable morphological attributes. For this benchmark, we utilized 2 different cross-spectrum microscopes, multi-cameras and multiple resolutions. Furthermore, to localize and classify the WBC with the morphological attribute predictor, we propose 2 multitask detectors. One is the fully supervised and the other is sparsely supervised. Leukemia is the 10th most frequently diagnosed cancer worldwide. Due to its rapid progression, leukemia can diverge quickly. Plus, it is a leading cause of a cancer-related death in individuals under 14 years of age. Generally, for the diagnosis to prognosis of leukemia based on the 5 steps. Start with the physical examination and the initial medical tests such as the CBC and the peripheral blood smear analysis for the diagnosis. Flow cytometry, immunotyping and the bone marrow biopsies are used to confirmation and prognosis. Finally, cytogenetic and the molecular tests help in risk management and the guide treatment discussion, including dose management. But the microscopic analysis of the peripheral blood film offers a rapid and valuable diagnosis option in many settings. Additionally, morphological analysis aids in the early and accurate diagnosis of leukemia. But the microscopic analysis have its own limitation. The first one is it's knowledge intensive and the second one is the unavailability of medical experts, especially in the remote region areas. And finally, it's prone to error and the false positive and the false negative rates vary from 3 to 30% approximately. Due to the advancement in the AI can assist the medical expert to increase the efficiency and accuracy, including managing the record as well. Optionally, AI can assist the healthcare taker to reduce the error and improve the diagnosis availability with the CAD system. For the detailed, precise annotation of the white blood cells, hematologists prefer the slide analysis at 100x resolution because the structure of the slide of the cells is much clearer at that scale. However, it is difficult to handle because of the emergent size, small field of view, and it is a time-consuming process because we need many field of views to cover the peripheral blood film. In contrast, at 40x resolution, we have a large field of view which is easy to handle because no need of emergent soil. That's why it is a less time consuming and we don't have to capture so many field of views. Furthermore, the hematologists prefer to use for the protein analysis. But at 40x resolution, it is difficult to annotate the morphological attribute because of the large field of view and the internal detail of the cell is not much clear. The performance of the CAD system is directly dependent on a large and a comprehensive dataset. Secondly, the implementation of the CAD system must be adaptable to the various settings. And the most importantly, to gain the trust of the medical professional, the diagnosis must be insightful. With the consultation of the medical experts, we highlighted the limitation and characteristics of the existing dataset. In terms of limitation, most of the available datasets contain only a single type of a leukemia, and there is not a single dataset that maintains consistent imaging across different microscopes. Plus, the majority of these datasets are based on the single cell images captured at fixed resolution. Only a few datasets include localization annotation. There is only one dataset that provides morphological attribute of cells, but even that is based on the samples from the healthy individual. And finally, most datasets include only a limited number of white blood cell classes. To overcome the limitation of the existing dataset, we have collected a large-scale multi-domain leukemia dataset consist of almost 28.8K images captured using 2 different type of a cross-spectrum microscope and 3 different resolution, and by using the multiple different cameras. For the comprehensiveness, we capture the dataset using multiple options. We utilize the 2 microscope, high cost and the low cost, with the high cost option being about 17 times more expensive. For image capture, we employed a mobile phone camera for both setup alongside specialized microscopic camera. Interestingly, the price of high cost average quality specialized camera is 47 times higher than that of the low cost eyepiece camera. For the data capturing, we implemented both an ideal setting and an optional setting. To capture the same field of view across multiple settings, we utilize the 4 camera, with 2 capture the field of view and the 2 webcam used for tracking the location across the microscope and across the resolution. For the ideal setting, we use the high cost microscope with the high cost camera, and for the optional, we utilize the low cost microscope and a low cost camera. For the WBC annotation, we annotated each WBC with respect to 14 different classes. For example, lymphoblast, myeloblast, abnormal promyelocyte and myelocyte, etc. And further, we annotate the morphology of cell in terms of 7 attributes. The size of the cell, what is the nuclear chromatin, the nuclear shape, cytoplasm to nuclear ratio, and the cytoplasm vacuole exist or not. The large leukemia dataset have 2 subtypes. First one is leukemia artery, fully annotated, and the second one is sparse leukemia artery, is sparsely annotated. In our all, we have complete bounding box annotation with 14 types of a WBC. For each cell, we have a 7 types of a morphology annotation. Now I am talking about the collection procedure of the leukemia artery fully supervised dataset. After capturing the same region at the different field of view setting, the hematologist annotated the highest quality image, and then we transferred those annotation across all the LCM and the HCM settings. For the sparse leukemia artery dataset collection, at 100x magnification, the field of view is small, but cell morphology is clear, visible for accurate annotation. However, in the corresponding 40x image, cell appeared much smaller, making annotation more error prone. To address this, hematologist annotated the slides at 100x, and those annotations were mapped on the corresponding 40x image. As a result, only about 1/5 of the 40x image at random location is annotated, while the rest remains unannotated. Now I am going to talk about our proposed methods. For the full supervised leukemia artery dataset, we propose attribute detector named AttriDet, and for the sparse annotated images, we propose the sparse leukemia attribute detector. Now I am talking about the architecture of the leukemia AttriDet. Now I am talking about the leukemia attribute detectors architecture. For the dataset, we capture the image from the microscopy slide, and in step 1, we use this image for the input of the WBC detector. The architecture of the SOTA detector is almost based on the 3 components: backbone, neck, and the head. For the WBC detection, we trained the detector using the standard losses function for class, bounding box, and the confidence score of the object. To include the morphological prediction, we extracted the features from the initial layer of the backbone. Using the ground truth annotations, we normalized the bounding box according to the extracted features and obtained the object feature from these. Next, we resized the features and concatenated them as an input for the small attribute prediction head. This head is based on the 3 convolution layer with max pooling. Additionally, we employed the 3 fully connected layers with the dropout, and a leaky ReLU activation function was used for all layers. Finally, we employed the symmetric loss for multi-label classification for the attribute in conjunction with the detector loss for the final training. For the sparse leukemia attribute detector architecture, to deal with the sparse dataset, in the first step for the WBC detection in annotated region, we trained the detector using the standard losses function for the class, bounding box, and the confidence score of the objects. Secondly, for the unannotated region, initially we select the high confidence prediction and extracted the pseudo labels and compute the pseudo label loss. Thirdly, for the medium confident predictions, we use the prediction including the ground truth labels and the extracted feature for the next section and compute the triplet loss to keep the same class's cell close and the opposite away. For the attribute prediction, we employ the same attri head with the asymmetric loss. For the implementation of the first component, first of all, we divided the labels into the three categories: low, medium and high on the basis of confidence score. Then we set the pseudo label selection criteria into the three steps. First one, we discard the prediction label that bounding box size is very small or very large. Second, we divided the labels into the three categories: low, medium and high on the basis of confidence score, and picked the high confidence prediction for the pseudo label. Third, we compute the entropy on the probability of the class prediction and set a threshold for the final pseudo label. Finally, we got some high quality pseudo labels for the unannotated region learning. For the implementation of the triplet loss, in our setup, annotations are available only for a small region, and the rest of the image remains unannotated. However, we utilize the prediction with medium and the high confidence that were not selected as a pseudo labels. Against each ground truth and the selected labels, we extracted the object features, and from the annotated regions, we set the object features as an anchor and treat the feature from the unannotated object as a positive and a negative samples according to the classes. Using this setup, we compute the triplet loss to enhance the feature learning. For the experiment, first of all, we conducted the experiment for the WBC detection from the baseline SOTA detectors. Secondly, we conducted the experiment from our proposed methods against the full supervised leukemia tree and sparsely annotated datasets. Lastly, for the comprehensiveness of the dataset, we conducted the domain adaptation baseline experiments. For the experiment analysis, we employ the different architecture-based approaches: sparse RCNN, a two-stage detector; FCOS, an anchor-free detector that directly detects objects from the features; DINO, a transformer-based architecture; and a YOLO, a single-stage anchor-based object detector known for speedy optimization. The object detector precisely localize the white blood cells and can predict their class, but they do not have the ability to further predict the morphology and characteristics of the WBC. We tested our baseline methods on subset from both 100x and 40x resolution, evaluating performance on both high quality and the low quality microscopic samples. The experiment were conducted using image captured with the mobile eyepiece camera C1 and specialized microscopic camera C2. As a result, compared to the fully supervised learning, the single stage anchor object detector performed well across most of the subset of the dataset. That's why in our proposed approach, we choose to use a single stage anchor based object detector. For the proposed attribute, we trained the attribute based on the YOLO V5X detector. Additionally, we employed the concept bottleneck model approach, which uses objects from the images to train a resonant 18 for morphology prediction. However, the performance of attribute was significantly better than that of the CBM. By adding an extra head for morphology, the performance of the detector is also improved. This indicates that the robust feature learning using the attributes head result in improved detection. For the proposed SLADET, we used the sparsely annotated subset and trained the sparsely object detector. Additionally, we employed the sparse stat and co-mining approaches, which uses the sparse annotated data for the training. However, the performance of proposed SLADET was significantly better than that of the SOTA methods. In our proposed method, we have a multiple component. To demonstrate that each component, label region, pseudo label and triplet loss, is essential for contributing to the final accuracy of the model. During the inference, we utilized the prediction from the detector and applied the same procedure to detect WBC along with morphological attributes for every image from a PBF. We saved all predicted information corresponding to each detected cell and maintained the detection record name as a morphology bank. For the slide levels report generation against each slide, the captured image from the monolayer will be provided to the proposed detector, and against each image, the detector will detect the class and morphology attributes and update the morphology bank. For the final report generation, we compiled all information of the morphology bank to update the mask statement based on the annotated images and the detail of the morphology. As a result, we have a detailed statement that complete detection information along with the morphological attributes to facilitate the hematologist. For the domain adaptation baselines, we gather data across multiple settings with the cross-domain but similar objects, which may enhance unsupervised domain adaptation method. Multiple domain and multiple resolution dataset from the real-world problems can help improve unsupervised domain adaptation techniques and contribute to finding feasible solution. In our dataset, we have a different domain images, and this is the example of domain shift from the low cost setting and the high cost setting. For our experiment analysis, we utilize the low cost microscope with the low cost specialized camera and the high cost microscope with the high cost specialized camera subset of the dataset. We evaluate the performance and train two state-of-the-art method, confmix and data, and the results showed performance between the two approaches. We believe in reproducible research, so the source code and the dataset of the attribute and the sparse attribute is publicly available. I will encourage you all to use these dataset and methods. In case of any question, please feel free to reach us. Thank you very much.